Good evening to one and all here. I am Anupam and Anupam Kumari, and I am a PhD scholar from IIT Jodhpur. So my topic is conducting yarn-based capacitive humidity sensor. And we'll start with the presentation outline, which is motivation, then introduction. Then we will see proposed sensor structures, sensing mechanism, the readout circuitry, results, conclusion, and finally the references. So starting with the motivation, like humidity sensor finds its way into like various fields such as healthcare, food industry, agriculture, fuel, and obviously the aircrafts. So, and here we are making this humidity sensor based on conducting yarns. Why we have selected conducting yarns? Because it has several advantages such as the cost effectiveness, they are light in weight, they're flexible, they're washable and reusable. So all these advantages makes it a very suitable candidate for using it as an application for smart wearables and can contribute to Internet of Clothing like Industry 4.0. So let's start with introducing the conducting yarn. It is a yarn that can conduct electricity, basically a thread that can conduct electricity. Then each of the fiber or the strand of this yarn has a diameter of 10 to 50 microns, and these yarns are of three types. It can be divided into three categories. Firstly, the conducting material itself, a thread made out of conducting material. Secondly, a blend of conducting material with some insulating polymer. And thirdly, coating the existing threads, suppose cotton or nylon, into coating conducting material on the existing threads. So we can pattern these conducting yarns like normal yarns only, like embroidering, weaving it. It can be sewn, felted, braided, or knitted. And so here in this study, we are like embroidering. We have used the embroidery technique, and our conducting yarn is a blend of conducting material and insulating polymer. The conducting material is tungsten, and we have the insulating material as polyamide and pyramide. So here is just a small experiment which we have shown in the figure where we have given a 3-volt supply to an LED and the circuit was kept open, and we have closed the circuit using conducting yarn. It just shows the conductivity, electrical conductivity of the yarn. So the figure A, B, C, and D are showing the FSM imaging of the yarn, where the overall diameter was 230 micrometer. Each of the strand of this yarn measures around 12 microns. Then the tungsten core filament is used here, which is of 30 micrometers, and the specification is 33 TX, which means the 100 meters of the yarn, 1000 meter of the yarn weighs 33 grams. So it is very lightweight. Here are the proposed sensor structures. For simplicity, we have named it as like A, B, C, and D, that is parallel plate, a parallel plate, cotton coiled, and C is jute dielectric based. So the first one is very simple. We have just embroidered 2 electrodes out of the conducting yarn. The black one, which we are seeing here, is the conducting yarn on a cotton cloth substrate, which is white in color. So the above images is the real images, and we have just for to make things clear, we have make an immediate image of the same. The second one is cotton coiled. So firstly, here we have placed a conducting yarn on the cotton cloth, and then we have spiraled, embroidered it on the cloth, and then the second layer of the same yarn, parallel to the first, was placed, and then both was spirally embroidered fixed. So the distance between the 2 yarn is just 1 cotton thread. And the third structure is jute dielectric based, where similarly 2 parallel plates are made, and the area between those 2 were filled with jute fibers, and then it was fixed with cotton thread. So these are the 3 structures. The sensing mechanism here is very simple. That is the 2 electrodes of conducting yarns on a cotton substrate, cotton cloth substrate. And the distance between 2 is the obviously porous hydrophilic material, that is either cotton or cotton thread or jute material. And whenever in the presence of water molecules in the air, these water molecules get trapped by the hydrophilic fibers present as a dielectric, and we change the dielectric, and the sensing mechanism is simply the change of capacitance with respect to the dielectric. So this is the overall sensing mechanism. Here's the readout circuitry. We have made the readout circuitry using ESP8266, and the OLED display is used to flash the humidity inside the sensing chamber, the temperature inside the sensing chamber, because temperature should not vary. We are just varying the humidity. And then we have placed our sample yarn, sample sensor, and it also measures the change in capacitance of the sensor in test. So the data output is recorded using I2C protocol, and the values are collected from data logging using comma-separated values format. Here is the result. The graph here shows the comparative result of all three sensors, which clearly shows that the cotton coil sensor shows the best response. And we can also see that the parallel plate and jute dielectric based sensors are showing almost similar result for lower relative humidity, that is below 70%, and above that the variation is changed. And also all the three sensors, for all the three sensors, the graph follows two trends. First one for lower humidity, and second for higher humidity. So for lower humidity, that is below 70%, the graph for both parallel and jute dielectric based, parallel plate sensor and jute dielectric based sensor are found to be same. So here is the tabulated result of the same. We have valued it just to show the slope for the sensors. So we can see here that for lower humidity, that is, I'm mentioning lower humidity, the humidity below 70% and higher humidity above 70%. So for lower humidity, the slope is 0.46 picofarad per decade, and for higher humidity, the slope is 3.8 picofarad per decade. So from 40 to 70%, the change in capacitance was found out to be 4.6%. But when we move for higher relative humidity, the change in capacitance was 38%. So from 4.6% to increase has been recorded to 38%, which is quite appreciable. So with that, I'd like to conclude the presentation with a note that the design capacitive sensor was found to be more sensitive for higher relative humidity. It can be used as a application for high humidity sensing. So the weaving pattern of the yarn, as we have seen that we have used 3 weaving patterns, and all the 3 weaving patterns shows different results at some shows different result at higher relative humidity. Some like cotton coil was showing seemed to be more sensitive for all the humidity. It was showing a great result. Then again, the use of conducting yarns for various applications may find its application in various fields, because it has some unique properties like portability, ease of use, and durability. And also the area of this conducting yarn is quite recent, and it has lot more scope for improvement and usage, as it can be one of the contributor to the industry 4.0. So these are the references. And I'd like to acknowledge research and innovation in multidisciplinary sensors. Then Jodhpur City Knowledge and Innovation Cluster for the financial support, and Ministry of Education India for my PhD assistantship. Thank you.